All right, so we need to look at least, not in gory detail, but really need to understand a bit more about quantum numbers, a little bit about where they come from, but I really want you to get the basics of quantum numbers and how to use a periodic table to figure out quantum numbers for particular atom or particular electrons. And really, okay, so anyway, what quantum numbers come from is it's called wave functions, wave equations that we use to actually describe mathematically what happens to electrons around an atom or even around molecules. These are complicated sets of equations that so where we can solve for how the electrons behave or how they probably behave. Telling exactly where electrons are, how fast they're moving, those things are a little bit tricky to do. For some things, actually impossible. But and this is what the wave functions are dealing with. And again, we don't need to worry about details of this. You're not going to have to worry about solving these. But I do want you to know that when we call the quantum numbers we're talking about come from mathematical calculations that we use to try to understand a little bit better about how atoms behave. So there are four main quantum numbers, and there are calculations you can do to relate one to the other. Basically, the first quantum number is the principal quantum number. It indicates the overall energy. Sometimes this is called energy level, sometimes energy shell. The terms are used synonymously, so be careful about those. And when it's called energy level, there are electrons in an energy shell or level that have very similar energies. Not identical in many cases, but very similar, very close to each other. And these quantum numbers are n equals 1 to infinity. So we'll discuss this in a little bit more detail, but so the quantum number n is going to be 1, 2, 3, 4, 5 up to infinity. The second quantum number is called the angular momentum quantum number, abbreviated with an L. And this actually, well, what it does for us is it tells us how many sublevels or subshells there are in a given shell. And this shows L equals 0 to n minus 1. What that means is if n equals 1, L can be 0, and that's it. So n minus 1 is 0, so you go 0 to 0. If n equals 3, L goes from 0 to 1 to 2, which is n minus 1. So there are 3 sublevels in the third energy level. It actually also tells us the shapes of these levels, or the shapes of the orbitals, but I think the number of sublevels is probably a little more critical. We'll discuss shapes in a bit. Magnetic quantum number indicates the number of orbitals in each sublevel. And m goes from minus L to plus L. Basically, you can use this to figure out how many sublevels or how many orbitals are in a given sublevel, and you can memorize these relationships for L and for m, or m sub L if you want to. But it's going to be easier. I'll show you in a bit how to get that from the periodic table. I think that's a little bit simpler than trying to memorize this and getting it messed up. At least if you go through these equations, then we'll use the periodic table to reinforce that you've done it correctly. Because it's kind of easy to slip up sometimes with that stuff. And the last quantum number is the spin quantum number, which indicates that really the one thing it does for us is that each orbital only holds 2 electrons. And this tells us it's like, think about each orbital as being like a step on the energy scale. It tells us how many electrons can occupy a given energy. Once that level is full, you got to go up to the next energy level up, and so on. So this means we can't pack all the electrons into the lowest energy state. So it really tells us we have a limit on how many electrons can exist in a certain energy state. So energy shells, or levels as they're called, these are basically 3D regions around the nucleus where we can probably find electrons. Again, even though we've done some nice advanced calculations, we don't know exactly where the electrons reside. We can't tell exactly. We can only predict where they're probably going to be found. So we'll show you the shapes of these regions in a bit. And again, these shapes are where we probably can find the electrons. And as I said on the last slide, the shells are distinguished by quantum numbers, integers, positive integers 1 through infinity. And all electrons of a particular shell tend to have, do have very similar energies. Not always identical, sometimes they are. But as you get to higher numbered shells, they kind of overlap. So you can have energies of or electrons in one shell. In the third shell, for example, some of the higher energies in the third shell can actually have less energy or more energy than the lower levels in the fourth shell, and we'll show you that in a few minutes. So each shell has a maximum number of electrons it can hold. And this again comes down to each shell has a maximum number of subshells. Each subshell has a maximum number of orbitals. Each orbital only holds 2 electrons, so there's a maximum number of electrons in each shell. But what's good to keep in mind is that the lower shells are physically smaller. We'll show you in a second. The s orbitals, for example, are spherical. So the 1s orbital is a certain size, the 2s orbital is larger, and so on. So lower number shells are physically smaller, so the electrons in those shells reside closer to the nucleus, closer to the core, to the protons. Lower number shells also have lower energy electrons. These are the more stable electrons. They're going to the lowest energy state possible. And these are the ones that are filled up before the higher energy states. So electrons want to go to the lowest energy state possible, which really makes sense because the nucleus is positively charged, electrons are negatively charged, so the electrons want to get close to the positive charge. So they get as close to the nucleus as possible until those spacers are filled up, then they go to the next space out. Each shell has at least one sublevel or subshell. Now subshells, again we mentioned the energy shell or levels labeled 1 through infinity. Subshells are also labeled by quantum numbers 0 through n-1, but that gets a bit confusing sometimes, so we use letters to designate the sublevels or subshells instead of numbers. So instead of 0, 1, 2, 3, 4, we say SPDF, and then it goes on after that to GF and something else. But anyway, I think a quick and dirty way to remember this, and this will help you when we get to the periodic table, is the first shell basically only has one subshell. The second shell has 2 subshells. The third has 3, the fourth has 4, and so on. Fifth has 5, sixth has 6. So that makes it nice and easy. And if you remember, really we almost never deal with the G. If you remember the order SPDF, you really need to know that order for the SPDF subshells. The first shell only has one subshell, so that's an S. Second one has an S and a P. Third has an S and a P and a D. Fourth, SPDF. Again, all this comes from these equations back here underlined in red. But this is one time when I think instead of memorizing equations, memorize SPDF, and I'll show you how to use that with the periodic table, and it makes a lot less memorization for you. And it will help you understand better why the periodic table is arranged the way it is. So each subshell has a fixed number of orbitals. This comes from our third quantum number. The S has 1 orbital and is spherically shaped. The P has 3 orbitals, lobe-shaped. D has 5, F has 7. And again, these are things you can memorize. But when we get to the periodic table, not a very good overlap. Anyway, when we get to the periodic table, you'll see how you can get the number of orbitals from the periodic table. As long as you remember that orbitals always hold 2 electrons, we can get this information from the periodic table. So that makes, again, less memorization to have, but you still need to know SPDF in that order. Represents the 0, 1, 2, 3 subshells. The G we don't use as far, and in this course, it doesn't involve any naturally occurring elements. We use that more in spectroscopy and other analytical techniques. And so this shows basics of how this is broken down. Help you see a little bit better the value of n. For n equals 1, we have only one subshell. That's a 0, and we again denote this by an S instead of 0. So one subshell, one shell each. For the second energy level, we have 2 subshells, 0 and a 1. So we have an S and a P instead of saying 0 and a 1, and so on. M really tells us numbers of orbitals. I should go through that, I guess. S subshells have 1 orbital. P subshells have 3 orbitals. See down here. D subshells have 5 orbitals, and so on. So we'll go on and discuss it in a little more detail again, how this information comes out from the periodic table. Again, these are the quantum numbers, -3, -2, -1. Oops, come back there. And so for the values of m sub L, which tells us the number of subshells, but we don't really need to worry about those numbers in particular. Really, we just want to know how many orbitals are in a particular subshell. And again, we can get that from the periodic table. So I'll go through all that in a little bit for you. I think it's good first to visualize what these orbitals look like. And then they'll make a little bit more sense. S orbitals are spherical. P orbitals are lobed. And these are the two really that you need to be aware of. Sorry, I'm not drawing very well there. The D's and F's get some really funky shapes. I'll show you those, but don't worry about trying to memorize how they look. The S's and P's are very important when you get to 1 to 5 and hybridization of orbitals. You need to understand these. And so, the book talks about the nodes. This is a bit more complex than I think you need to know for right now. What this is trying to say. This is showing that as you go out from the nucleus, this is what this means. As you go out from the nucleus, the electrons can be found along. This is the probability of finding electrons in this region. So near the nucleus, there's a probability of finding one here. As you go farther out, you'll probably find them here. But the overall shape is still spherical. And I think that's really what matters, what's more important for us right now than trying to visualize the internals of these spheres. S orbitals are spherical in shape. The 1s orbital, these are the closest the electrons can get to the nucleus. This 2s orbital have the same shape, they're just physically larger. So the electrons in the 2s are going to be farther away from the nucleus than the 1s. And the 3s is the exact same shape, but it's just the electrons are farther out. The p orbitals, they lie along the 3 axes. Each atom has, we'll go back to here, each s sublevel only has 1 orbital. Each p sublevel has 3 orbitals. And they go along each axis, one along the x, one along the y, and one along the z axis. And they're these lobed, or some people call them dumbbell shapes. Again, these look more funky, especially this one over here on the far right. S, I thought I had some F's here. They're even weirder shapes. But that gives you an idea about the basic shapes of the orbitals. And remember, each orbital only holds 2 electrons. So, this p orbital can hold 2 electrons, this can hold 2, and this can hold 2.